Hi everyone, my name is Mark and I'm the creator of a floating face project, short Floaty, which is a free cable mounted roboter just, I don't know, moving around in a room, I guess. But the nice thing is it is portable, you can just take it with you and mount it on any 3 points and it will do what you say it to do. So today we are going to talk a bit about the mathematics, algorithms, calibrations, and problems, I think, about like what I encountered while designing Floaty and the thoughts behind Floaty. So first of all, Floaty is just basically the platform for a more complicated system, I'd say. Floating face comes from the name floating interface, and I just wanted to make it a bit shorter, but I'm not very creative person, I guess. So why floating interface? It's just very simple. If you look at the model, you will see that on the bottom of Floaty, as I like to call it, on the belly of Floaty, is a cheese plate, which makes it possible to mount different systems. On the top, in the first level, it's the motor level, there is also a servo from Waveshare. Yes, from Waveshare. A Waveshare servo which is able to power mechanically everything you mount on the bottom of Floaty. So I think the design is for another video, but we are going to focus on mathematics today. So basically Floaty's task is to get from point A to point B. To be more precise, from point P0 to point P1 in our context, because the 3 points on which Floaty is mounted are called A, B, and C. Mathematicians, please don't kill me. I am going to name the points not like conventionally. I don't know how I don't even know how the normal people, like normal mathematicians, do it. I just like named it from left to right, A, B, C, just for me to remember it better. But anyway, so basically we want Floaty to get from point P0 to point P1. And how do you do this is actually much easier than you think. Floaty has 3 motors. One going to A, one going to B, and one going to C. And we basically need to send, based on our input of P0 and P1, yes, you need P0 too to move it, to process it into commands for every motor. So the first thing you need to know is P0, and that is achieved through the calibration process. But about the calibration process is just another whole different topic. It will be later in this video. We suppose that we know P0 and we want to get to P1. I've drawn it in a 2D projection from the top, if like this is a room. Then it's just like from the top, this is the floor. But you can also draw it like from side view. We are going to take the points A and C. Don't kill me about the proportions and about the margins. And yeah, let's say another example, P0 is here and P1 is here. So very simply explained, it does just calculate the vectors, and let's do that. To get from P0 to P1, let's just look at A. We need to reduce the length of the cable. I don't know if it's really reducing it here. Maybe it's just a bad example. Let's take C. Here. Let's take C. We need to reduce the length of a cable from C to P0 to the length of the cable from C to P1. I'm not drawing through the letters. You're not going to see me demolish my wonderful writings here. So basically what we do is we just take the vector from C to P0 and calculate its length. And now we take this length and subtract it, and from it we subtract the... No, I'm very sorry, we subtract from the new length the old length. and you will understand why. This is counterintuitive, by the way. CP0, a vector, yeah. Why are we doing this? Very easy, because we need to get, also we can get a negative value. This is very important. It is because if everything would be positive here, all the motors would just like give the cable. I'm going to use the words give and take to just like get the rope towards the points or just like back. To tension it or to loosen it, exactly. These words is what I searched for. So if we have a value n, no, let's suppose these are just our values. So you see, it's pretty intuitive that P0 is longer than P1. And if we subtract from CP1, I don't know how even to pronounce it in English. If we just do this operation, we're going to get some negative number, negative n. If we are having B, for example, oh no, I have to draw through the formulas. Anyway, if we're having B, so our BP1, BC1, we're going to get a positive number, a different one. Let's call it M. Why? Because BP1 is longer than P0, and you need just like to take cable. It's somewhere like an inverted operation, I guess. I don't know. I just like graphically drawed it also here and just concluded, yeah, that's the correct thing to do. So yeah, that is actually how it works. And these differences are, we are going to name them delta Gn. Why delta Gn? Delta is first of all my favorite letter in the Greek alphabet. I don't know why. But delta also means the difference between two things. And Gn, I first called all the motors a motorization group. And that's why the G came in. And later it just like stayed. I don't know why, but I just did it. And the N is like another motor, which we are explaining. So if you look through my code, you will see sometimes some methods will be called delta G and something. But anyway, let's move on to the vertical simple feature here, to this vertical operation of Floaty. It's the same thing here. You just take these two vectors. By the way, we need arrows here for these are vectors. And do the same calculation, and you will notice that it's just the same. You do calculate just the difference between the vectors, between our anchor points and the motors of Floaty, and you just need the difference to say to the motor, yeah, run back or run for, just like give or take a certain amount of rope. So first, I thought, yeah, it's pretty simple because I always know how much steps my stepper motor gives. One thing I didn't account for was that the rope is winding. Let me show it to you. So if we have a drum and the cable drum and the cable starts winding here, the radius of this cable starts getting bigger. So therefore, when we have when all our cables winded up and the distance between like the anchor point A and Floaty is small, then one rotation of this motor is going to result in a bigger give or take. But if we have a big distance, say between B, then there is going to be less cable given or taken. I hope this is understandable. There isn't a problem to calculate this. The problem is in theoretically it is calculatable, but practically it's an absolutely chaotic process. So you really can't predict how the rope is going to develop inside, except you have a rope guidance system, but it's another topic and it was just too complicated. So I settled down on a different solution. I settled down on taking this drum and putting a smaller guide before it and just getting a sensor on the axis of the upper guide so that when the rope goes from here, we just exactly know how much rope is given or taken. Even when knowing how much we move where and how much each motor or floaty needs to move, we still encounter a small problem. It is that our motors run exactly equally fast. So what happens is our motors are stepper motors and they give pulses that if, let's just, no, why am I doing it like this? So if we draw the steps, the impulses from a motor, they are going to look like this. This leads, so in some cases, that's not universal, this leads to the fact that these motors end at a different time. And that's not good for us, because when this happens, Floaty starts to tilt. Imagine you're a videographer just mounted a new camera on Floaty, and Floaty starts just like tilting while it's moving, and you can't get a steady shot. Horrible, isn't it? Therefore, we need something called time-controlled movement coefficients. So what we actually want to see is something like this. Yes, that's something we want to see. But how do we achieve this? We achieve this by changing the time in between the pulses for each motor. So within one motor, the time difference between all the pulses stays the same, but the time difference between each motor is different. So how do we achieve this? We achieve this by taking the basic coefficients. So first of all, we need to find the one with the maximum, the one with the maximum run, so the one that needs the most distance. This is going to be our key value. We're going to orient all our timing of the other motors based on this one motor. And with that, we are going to calculate the coefficients. The coefficients are calculated in that way that we take our biggest value, it's A for example, and the coefficient for A will be A divided through A. For B, it's going to be B divided through A, and for C it's going to be C divided through A. So this is what it looks like. This is our all coefficients. So right now the coefficients look in our case something like this. It's something like 1, it's here something like 0.5 and like 1/4. It's just like this is 1/2. Something about that. That is not sufficient enough because we actually only need the bottom number, if you say it like this. So while the pulses here are always 1, they should be here 2, and here they should be 4, something like this. We do achieve this by just like dividing 1 by taking 1 and dividing it through our coefficients. That's also the wrong numbers. Let's say the coefficients are C delta N. So therefore we get our set, or a vector. Actually, you could say it's a vector. I've represented it all in C++ when programming it in arrays and with 3 values. Therefore, it's mathematically somewhat describable as a vector. And by that we gain our time difference coefficients. That is so far pretty easy. While I was explaining to you, I noticed that I forgot to implement that one divided through in the program. So anyway, that will be fixed. So suppose that we managed to do all of it. We managed our algorithms. We managed to implement that all. There's one question left. Where the hell is Floaty? Floaty is at P0. But where is P0? P0 needs to be found. And it needs to be found when Floaty is in any position, when it starts working in any position. So before we start calculating our movements, we first do the calibration. And the calibration is what I call the TDC, torque-driven calibration process. This is achieved by taking... I'm writing the wrong letters. We do this by making one motor a main motor and the other slaves or followers, and let our one motor produce torque and move. As we use Team C2209 servers, they are able to measure somewhat relative torque, but it's not like given in Newton. It's a value between 0 and 500, and when it's 0, the motor is stalling. So we make one motor pull, and the others, when they feel that they experience a certain higher torque, they are just following. They are giving rope. And by that, at some point, we will find Floaty at point A. It will be here, and it will be pushed with its bumper. I've added bumpers to Floaty for every motor. Again, the motor starts to experience a very high torque, somewhere near the 0 value, and it knows, yeah, I'm at point A. That's my point A. When this happens, the most calibration process is already finished. But now, as I've said, we can mount Floaty anywhere. To mount it anywhere, we need to know the distance between A and B and C and A to be able to construct this triangle digitally. When we have all this value, we can construct this triangle. So what Floaty does now is Floaty is doing the same process, but the lead motor is B. It's the motor B. And therefore, what happens now is that I've forgotten, AS5600, that's the name of the magnetic encoder, starts reading. And after it stopped reading, we can just convert these angles it collected to centimeters. And now we know, yeah, this distance is X centimeters. So if we know it for all of these 3 sides, we actually know how this triangle is built, and therefore we can just start dividing factually, calculating all the coordinates which we can address inside of this triangle. Because we can't just address the coordinate, we can make P1 here, because otherwise Floaty would need to somehow, I don't know what to do, it needs to use the elasticity of a rope, Sven, and make itself go whee! But it won't do it because I don't want it to experience high g-forces. So this is the torque-driven calibration process. And what are the flaws? The flaws are the construction. The flaws are simply that the whole system needs to be rigid because you do torque, TDC, torque-driven calibration. Therefore, your system shouldn't break under load. And that is what is left to determine. I said it's sadly very hard to calculate the exact values for 3D printed parts, and Floaty is mostly 3D printed, how much torque they can experience before braking. And that is what I will going to determine, and that is what I'm going to program and what I'm going to fix when I have Floaty built. So yeah, you just heard a 17-year-old brag like, I don't know how much it is, 20 minutes about his robot, which isn't built. It's just like all theory. So even if my project doesn't get approved, I want to thank Blueprint, because it was a motivator to do this project, and it was a huge motivator to gain more knowledge. I've simulated this whole process in Simulink, and this was already an experience for itself. It was already something I would probably never done if not Blueprint. So yeah, thanks for watching. Thank Blueprint. Thank you, and goodbye.